So now we'll jump into your k-means clustering. So k-means clustering, as we had discussed, is nothing but a popular partitioning method similar to the previous techniques which you have used, but it's more of actually natural data partitioning, right? So we'll be using the base k-means package, which has a k with a small letter. Alternatively, there is a k-means which has a k capital, which is part of the AMAP package. So we have to get the data. So just trying to get that. So let's say variable name WSS. And you can say, so what you're doing is you're doing some kind of standardization over here. My data minus 1, and you're multiplying this by the sum of apply function, wherein you're passing my data as a data, comma 2, comma vr, and then you're saying for loop. So it makes sense to draw this for loop in a code editor rather than typing it over here. So I'm coming over here for I in 1, sorry, from I in 2 to 15, saying the loop WSS box bracket I, accessing the index, allocation sign, and here you're saying sum. It's a functionality. K means my data, comma centers is equal to say I dollar. So for different values of k, you are basically trying to compute the sum of squares. I'm just going to run this. Right. And then you can view WSS. Let's just add one more functionality over here. It's not clearly shown that it ends over there. Plot 1 to 15 WSS type is equal to both, that means a line and a point. X lab is equal to number of clusters, comma y lab is equal to within group sum of squares. And so you can see this over here. So as your number of clusters are increasing, the within group sum of square is reducing. Now you need to take a rational call as to where you will optimize and say that okay, this at 13 number of clusters as compared to 14 and 15, I'm getting the same level of sum of squared error, so I might select 13 as the optimized number of clusters which I want to draw. But for some reason, as you can see in your data, they have said that 5 clusters is the best one, right? So we'll go with that notion because it's a demonstration and not uh, uh, actual implementation, right? So had it been any actual implementation, we would have gone on a different level. So now let's plot this. So I'm just going to close this part over here and just running it again, just clean this all stuff. So I can say fit allocation sign k means, and this you're going to save in a fit object, my data, comma 5. You're not passing anything else, you're just saying 5 clusters, right? And then you create that cluster. Now you can say aggregate, right? And in that you can say my data, comma by is equal to list. So you want aggregation by fit dollar cluster, and the functionality, so we are saying fun is equal to mean. So enter. So you have these group, so you have 5 clusters, right? And you have got these various mean values for those clusters, right? Now you can also try it with the fit object directly, right? This also would be giving you the same value, right? Because this is by default saved in the object, and this is something where the programmer wants to aggregate by mean. It depends how you want to use them. Simple is always better. If it's already provided there, it doesn't make sense for you to compute, right? But still, as a programmer, if you want to do it, you can do it, right? Now you can assign these clusters back into your data, so you can say my data, but you will have to give it a name, right? So say, let's do it this way first. My data dollar cluster number allocation sign fit dollar cluster. Okay, this is a different object, so let me try this. Allocation sign data dot frame my data comma fit dollar cluster new my data. Okay, now you can plot and validate the cluster so that you can visualize it, but ideally it doesn't make sense to visualize a cluster, right? Because we know how a cluster works, but still if you want, and if somebody wants to go ahead and do it, so you can do it. So you can say fit, I'm doing it, say k means, and inside that I'm saying my data comma 5, right? And you can say cluster plot against first second principal components, right? So now this is where you are trying to create a principal component, because you cannot directly plot this, right? And that is why you're creating a multiple axis graphical image, and you just want to transform a couple of variables. See, it's possible to plot an x and a y, but if you have an if you have an x1 x2 x3 x4 x5, then obviously you cannot show that on a plot. So that is where the components are being transformed, so that you can have a look at that. But ideally you are not in a position to analyze that back and make an inference. But yes, if somebody wants to anyway visualize this, so there's an option available. Class plot data comma fit dollar cluster comma color is equal to true comma shade equal to true comma labels is equal to 2 and lines equal to 0. So for this data, it's not allowing us to do this, and call x so number of observations is less and number of variables have become very large. That's why it's not able to plot it. So let's try the other part, library fpc plot cluster my data comma fit dollar cluster, right? So this is where you're plotting the clusters. This is the center points. and you have cluster, so cluster dot stats, and that you're passing d comma fit $1 cluster comma fit $2 cluster. Now when we are looking at fit 2, it is not giving us anything, so I don't think so it will come. So what you're seeing on the screen is like a fit 2, but we haven't done a clustering for the fit 2 cluster, so ideally it won't come over there. So just pass, these are the cluster values, so you can just have a look over here. So it's the number of observation, cluster numbers, total number of clusters, the sizes of the cluster, 7 cluster, so 7 observation, 12, 13, 7, 11. Minimum size cluster is 7, that is this cluster, and this is the entropy, and this is within cluster sum of squares, the minimum separation between the clusters, the max diameter